So today I'm going to apply Frobenius splitting method to the geometry of Schubert varieties. I will present the notations and the results only for the general linear group, but you can extend widely all the results to any semi-simple algebraic groups. So GLN is not semi-simple, but it's not so far from SLN, at least for those that are familiar with their structure theory. So let as always K be algebraically closed field of characteristic P positive. So for today the group is GLN, so N greater or equal to 1, so GLN okay. Set B Morales subgroup of G, so you may take here a triangular upper matrices. And we consider X as G mod B, called the full flag variety. So it is known that it is a projective, smooth, and you can compute the dimension of dimension n minus 1 over 2. So let's say in a more concrete way. So so define a complete flag D to be a D node, the zero vector space containing V1, containing V2, so a sequence of vector spaces containing Vn, with the condition that the dimension of the Vi is exactly I. So let's choose E1 up to En be the standard basis of K to the N. So G, the group, acts on this vector space. So you get the, say, the standard flag. So V I'm not sure this is a standard name, but it doesn't matter. So this one is 0. So V1 is generated by E1, and so on. Vi is generated by E1 up to EI, and in the end you get Kn, and you see that the group G acts on the set of flags, and the stabilizer of this one is precisely the Borel subgroup. So in this way, you can see that G mod B is exactly the set of complete flag. So we consider the Weil group. So we saw that this is a symmetric group on n letters. So we see it as, again, acting on the bases. And so this was the definition this morning. So let omega in the Weil group, so in the symmetric group, and define, say, the Breuer cell C omega to be, so first you consider the standard flag. W, so acts on the basis, but W may seen as well as contained in our group G. So it acts on the flag, and you consider the B orbit. Okay, so this is nothing but B omega B mod B. So this is the Breuer cell, and the Schubert variety X omega, so this is a definition, is the closure of the cell in G mod B that is projective. So let's say, again, in a more concrete way, C omega can be described as follows. So this is a set of flags, of complete flags. Such that, so we get some condition on the intersection of the flag with the standard one. So such that the dimension of VP with VQ standard is exactly the number of ij, no, the number of i's such that omega of I is greater or equal to 1 and less or equal to q. This is for all P and Q. And similarly, the Schubert variety is exactly defined by the same, in the same way, so, but here greater or equal to the same number. P, oh, sorry. So this is not the same P. So this is Q1, Q2. P is not prime. Q1 and Q2. So this has nothing to do with the characteristic. So example. So define SI exchanges I and I plus 1. So this is the identity elsewhere. So I now So this is a transposition. So what is XSI? So say if Q1 is equal to Q2, and these are less than I minus 1, less or equal to I minus 1. Omega Si is the identity, and the condition is exactly that the dimension of the intersection is maximal. They have to agree. So for P less than I minus 1, Vp, no, not P, for Q less than I minus 1, Vq has to be exactly the standard 1. The same is true for Q greater or equal to I plus 1. So in the end, you get that this is a set of complete flag such that so dq is exactly dq standard for q different from I, and so this is exactly the q standard. This is the I minus 1 standard contained in di contained in the I plus 1 the standard 1, so E1 up to EI plus 1. So VI has dimension 1. As dimension I, it has to contain this vector space of dimension I minus 1, and has to be contained in this one of dimension I plus 1. So you see that this is exactly a P1. Okay? So these are called the Schubert curves. Maybe the first one I should have give before. Consider omega node to be the permutation that maps 1 to n, 2 to n minus 1, and so on. So you see that this is an involution. So you can check that this is the full flag variety. So there is no condition on the flag in that case. And finally, the Schubert divisors. So now you want to understand X omega Si. So you see that something happened between I and I plus 1, where you have a permutation, and you can check that. So essentially it says nothing before, nothing after, so you get only one condition, and you can check that this is exactly the set of complete flag such that so this condition is the dimension of di with the n minus 1 I standard is greater or equal to 1. So this has dimension I, this has dimension n minus I. So in general, the intersection is 0 dimensional. Here we are asking this intersection to be 1 dimensional at least. You get a divisor. Okay, so we will need this later on. So I need to introduce the length. So let again omega in the while group. So the length of omega is exactly the number of inversion in omega. That is, you count the number of ij with So I is greater or equal to 1, less than j, less or equal to n, and the preimage of I is greater than the preimage of j. So for instance, the length of Si is 1. There's just one inversion. Exactly the dimension of this XSI, P1. And you can convince you that the length of omega Si is the length of omega naught minus 1. Exactly the codimension 1. So I need to now consider U. Again, the set of upper triangular matrices, but now you put 1 on the diagonal. So this is in G and N. So this is a maximal nilpotent subgroup. Of B. It's more or less clear that the U orbit of omega applied to the standard flag is exactly the same as the B orbit. Okay, so now we want to understand the Schubert cell. So we need to understand the stabilizer of omega applied to the standard flag in U, but this one is, say, U omega. This is U intersected with the conjugate of U under omega. Pick, say, an element in psi. So this is a matrix with coordinates U, I, J. And so you can, the multiplication by omega on the left or on the right is essentially exchanging either the lines or the columns. So you can see easily that U omega is defined by the equations U ij is 0 for I less than j and omega 1 of I len less than omega 1 of j. These are exactly the condition you get. Now you can consider the opposite, say U omega. So let U omega be defined by Uij equal to 0 if for I less than j. So this is inside B, inside U. So for I less than j and omega 1 of I bigger than omega 1 of j. So now the fact is U omega is a subgroup. And the natural map from U omega to the Schubert cell is an isomorphism. So you see that not the Schubert, the Breuer cell, you get an isomorphism. So you see that the Breuer cell is an affine space. Okay, in particular, C omega is smooth. But in general, the corresponding Schubert variety is not smooth. So in fact, one has the theorem. So there is a combinatorial condition on omega to check whether this variety is smooth or not. So this is due to Lakshmi by and Shandhya, 90. And the condition is the following: X omega is non-singular, so it is smooth, if and only if omega has no subsequence so of the same relative order as, so these are 3, 4, 1, 2 and 4, 2, 3, 1. So by this we mean 1 is mapped to 2, 2 to 4, 3 to 1 and 4 to 2. Okay, this is the notation for this permutation. So just an example. So for n is equal to 6, you consider omega as 6, 2, 5, 4, 3, 1. And this one contains 6, 2, 4, 1. And this is exactly this relative order. So this one is exactly the 4, 2, 3, 1. So X omega is not smooth. So now the natural question is, what can be said about the singularities of the Schubert variety? So again, this morning, Bertrand introduced the Breuer decomposition. So G is exactly the disjunct union over the element of the Weil group of B WB. So in particular, X G mod B is the union of the Breuer cell, and proposition. So So you can try to describe the closure of a cell in terms of this decomposition, and the answer is the following. This is exactly the union of the Breuer cell V for V in W and V less or equal to W. So here, this is the so-called Breuer order. So can be defined geometrically. CV V is less or equal to W if the closure of the corresponding cell XV is contained in the closure of the corresponding cell to W, but so this becomes a complete triviality. There is another way, there's a lot of ways to describe the Breuer order on the symmetric group. So one way to describe it just say that this is a transitive closure of so you start with one of the very special transposition we have already introduced. You say that SI omega is less than omega if, so the condition is omega, the inverse image of I is bigger than the inverse image of I plus 1. And you consider the equivalence relation generated by this one. Okay? So you get, using this, you get this decomposition. So this is used we will use this later on. Now I want to introduce an inductive construction of the Schubert varieties. So so first let's consider omega in the Y group and omega different from the identity from 1. Okay. So I claim that there exists an elementary transposition SI1 such that the length of SI1 omega is less, and in fact the length of omega minus 1. So you have to think about it, but if omega is different from the identity, somewhere there is an inversion. I'm just killing one of these inversions. Just you can do that, and you repeat. So applying this to SI1 omega, you get that you can write omega as SI1, SI2 up to SIL, where L is the length of omega. So you cannot do that in a unique way. In any case, the collection of SI1 up to SIL is called a reduced decomposition of omega. So what can be done with this way of writing omega. So one I introduced Pij as the subgroup of GLN generated by B and the elementary transposition Sij. So you can check, one can check, that this is nothing but B union B Sij. B and say at least geometrically Pij is the stabilizer of the partial flag partial meaning that some of the vector space is missing. So obtain from the standard one by removing, so this is the I. So okay, one. So this is the stabilizer in GLN. Okay. So this is the geometric meaning of this minimal parabolic, and GI mod B is nothing but the Schubert curve P1. Yes, thank you. Yeah. So now one can describe the Schubert variety in terms of the reduced decomposition and this parabolic, minimal parabolic subgroup. So in a so the fact is so you can consider first the Schubert variety associated to Si1 omega. So this one has the length of Si1 omega is less than the length of omega. You apply, you look at the p orbit of this one, and what you get is exactly omega. Okay, so you see that at least x omega is contained in this one, since Si1 is R square the identity. Okay, and in fact you can prove that this is exactly the product of the Pij mod out by B. So in fact the reason for that is I would say the following rule. So you are in a linear group, so you can compute everything by n. If you look at B, say Si C omega, so sometimes this is the Breuer cell associated to Si omega. At least this one is always contained in this orbit, but sometimes you get more. So you get C omega union C as A omega, and the condition is this: if the length of SI omega is exact the length plus 1 and this one. If not, that is if the length of SI omega is the length omega minus 1. Okay. This explains this inductive construction of the Schubert varieties. So now I'm going to introduce the main object, I would say. So a resolution of the singularities of the Schubert varieties. So keeping in mind this inductive construction, the so-called Bode-Samuelson de Mazur Hansen varieties. So as before, you start with omega in the Weil group. You consider omega SI1, SIL, a reduced decomposition. Omega. And you can consider Z omega bar. So the product of PI1, the same PI, up to PIL, mod out by B to the power L. So I need to explain the action where B1, B2, BL act on G1, GL by the formula. So G1, B1 minus 1, B1, G2, inverse of B2, and so on. B L minus 1, GL, inverse of BL. So at least you see that if you consider the product of these guys, you get something inside the Schubert variety. So now I'm going to give you the main properties of these varieties. So I won't prove anything, but it is very easy. So and it has nothing to do with characteristic P. So facts. So these varieties are smooth. Projective variety of dimension L. Maybe I forgot to say that the dimension of the Schubert variety, at least the Schubert cell, is exactly the length. Okay, so these are the same dimension. And this is even a B variety, meaning that B acts on Z omega as it acts on the Schubert variety, where B acts via the following. So take P. Now a point in Z omega is nothing but G1 up to GL B to the power L, and you B act by multiplication on the first factor okay. To the second point. For any subsequent V in the reduced decomposition of W, so you consider an ordered subsequence, there is a closed B embedding of the Bode-Samuelson de Mazur-Hansen variety attached to V into Z omega. So it's easy, I mean, at least to describe this embedding. So if V, if so S I G1 S I G M, then you map G 1 up to GM B to the power M 2. So you put 1 1 1. G1 is exactly the place corresponding to J1 and so on. B to the power L. So you add some 1 inside. So now we can consider the map. So you start from Z omega. So Z omega, so this is associated to the reduced decomposition SI1, SIL. And you can forget SIL. You go to Z SI1 up to SI L minus 1. So this is the natural map. So G1 up to GL BL is mapped to, you forget the last one. So this is a morphism, and in fact this is a B equivariant morphism. With fiber being exactly pi IL mod B, but we know that this is a P1. So you construct your Bode-Samuelson de Mazur-Hansen varieties as a tower of P1 bundle. Okay, so you get in that way the smoothness stated here, for instance, and you can make explicitly a lot of computation using this description. So maybe more interesting. Now we are going to consider the product map. Pi omega from Z omega to x omega, the Schubert variety, that maps G1 up to GL BL to the product of G1 up to GL. Yes, the class, this variety. So this is B equivariant again, and restricts to an isomorphism over the Breuer cell. So you get a resolution of singularities of the Schubert variety. And in fact, the picture is much more nicer. So now you define omega of J. So this is exactly the same reduced decomposition, but you remove Sij from the decomposition. So the length is one less. So you get, thanks to the point 2 and point 1, the omega J may be viewed as the subvariety of Z omega is a smooth divisor. So this is define the so-called boundary of Z omega to be the union of these divisors. Then so I will need this later on. So first Z omega 1 up to Z omega L intersect transversally at a unique point it's not necessary for what we are going to do, but at a unique point corresponding exactly to b to the power L, so 1, 1, 1, 1, 1. For any subsequence V in W. So we saw that ZV is contained in Z omega, but we can say much more. ZV is exactly the intersection of Z omega J for J for Sij in omega, but not in D. And if you define the boundary of the Schubert variety to be exactly the union of, to be first the complementary of the Breuer cell. So the union for V less than omega of CV, then you can check that the inverse image of the boundary of the Brion cell is exactly, this follows more or less from the point 4, the boundary of Z omega. And finally, we need to compute the canonical class. So this can be done more or less using this description as a tower of P1 bundle. So this is the point 6. So recall that X omega is contained in G mod B. G mod B is a set of flags, so it is naturally embedded in the product from I is equal to 1 to L of the Grassmannian, so say in the vector space of dimension n. Okay, so you map all the VI into the corresponding Grassmannian using the precurrent embedding. You get something in the product of P of lambda I, the standard of Kn, k to the power n. So here we have a lot of O1. So define a Land bundle on G mod B. So so for the G1n, you consider n minus 1. You put it back to the product, and then you restrict. So this is the meaning of essentially the tensor for G2n. So this is the O1 to the power n minus 2, and so on. And you end with O1 so this is a very ample line bundle. Okay. And the formula is the following. The canonical class of Z omega is so the pullback under pi omega. So pi omega maps Z omega to the corresponding Schubert variety. So pi omega of, so you have your Land bundle, you restrict to X omega. You put a minus 1 because the anti-canonical class tends to be very positive. And you have to tensor with the sum for I is equal to L, from 1 to L of the Z the divisor introduced before. Okay, so this you just have to compute intersection numbers essentially. For instance, using the description as a tower of P1 bundle. So again, this has nothing to do with Frobenius method. So now, if you remember what I explained yesterday, so this is, we get the following result. So this is due to Ramanathan. In 87. So with the notation introduced before, Z omega is split by sigma to the power p minus 1, where so sigma is a globalization of the anti-canonical class, and where sigma vanishes on all the Z omega j, or j equal 1 to L, and as a consequence, for any subsequent d of W, ZV as a subvariety of Z omega is compatibly split. So this last statement follows from the fact that Z omega can be described as the intersection, and the lemma on the first day. So for the proof, so first you consider sigma prime with value in this shift so you consider the canonical section. Then you pick sigma double prime in this part. So any section on Z omega P upper star omega of L restricted to X omega. Any non-zero section, or in any case, any section such that sigma double prime do not vanish on the very special point here, where it is. Yes, we know that the Z omega j intersect transversally on some point, so the only condition on sigma do not vanish here. And then you consider the sum of sigma prime plus sigma double prime in the anti-canonical class of Z omega, and you apply the theorem we saw yesterday. The zero locus of this section is exactly the sum, the sum of Z omega j plus something. So these guys intersect transversally at some point. Where is the right number? L is exactly the dimension of Z omega. And because of this condition, the rest, yesterday that called the Z, avoid this point. So you get a splitting, compatibly splitting all the Z. Excuse me, yeah. Sigma does not vanish at this particular point. And we saw maybe on Tuesday that if a variety is compatibly split with respect to the sum of divisor, it has to be completely split with respect to the intersection of all these divisors. So the intersection, the union, and so on. So, but at the scheme theoretical level. But here, maybe I should have wrote it. This is an intersection as a scheme. So this is not just said theoretically. But this is clear since everything is smooth and everything intersects transversally. So for that point, it's okay. So as a corollary, X, that is G mod B, is split compatibly with all the Schubert varieties so for the proof, so recall that X omega node is nothing but X, the whole space, G mod B. So you consider now Z omega node over X omega node. This is G mod B. So we know from the point 4 that this is a birational. And yes, this is birational, that's all. From the point, the second one or the third one, I don't remember, we know that Z omega embeds into Z omega node. We have a map pi omega node. This one is pi omega, sorry. This one is pi omega node. And you can check this is really a commutative diagram. So we know that Z omega node splits compatibly with all the Z omega. This is the previous result. And we saw maybe on Tuesday too that we get the same result, just assuming that downstairs, assuming that the natural pullback, so the only thing one has to check that this has to be an isomorphism. Okay. But this is indeed the case. This is a birational morphism and this one is smooth. So the push forward of the structure shift is exactly the structure shift downstairs.
But the map on the right is not isomorphism?
No. Generally not, I think. No. We don't know. Yes, and?
You said that the map from Z divided omega to X omega is an isomorphism outside the...
No, over the cell. So you have an open subset, this is the cell, and the complementary is exactly the union of the all over Schubert varieties. And this point, more or less, say that above you get all the...
Even if the Schubert variety is smooth, you change the boundary.
Yeah. I something. Yes, the statement here says precisely that you can reconstruct all the z omega from the biggest one. So you can push down the splitting here. Okay, so now can we say something on the singularities? Yes. So the theorem X omega is a normal variety, and pi omega from z omega to x omega is, so I will explain what it is during the proof, is a rational resolution of the singularities. Of x omega, and in particular x omega is Cohen-Macaulay with a canonical class isomorphic to the being exactly the push forward of the canonical class of z omega. So being exactly so given by this. So in the end you get L minus 1 restricted to x omega tensor with O of x omega minus the boundary of x omega. So the proof for the first point is by induction on the length of omega. So first, if the length is 0, x omega is a point. There's nothing to say. So now let omega in the Weil group with positive length, and let Si, one of the transpositions that exchange I and I plus 1, such that Si, the length of Si omega is exactly the length of omega minus 1. So we saw a way to construct the Schubert variety by induction. So we are going to use this construction. So again, we call that Pi was the parabolic generated by B and Si. So B union B SIB, and consider now the map F Si depending on Si and W from so I will explain the notation. Pi cross X Si W. Here I put a B. Here you go to X omega. So what Here, this is just the quotient of pi cross x si omega by b, okay, where b acts on the product by the formula g to the power b minus 1 bx. So this is the action. The morphism here sent the point, the class of the point gx to the product. This is B equivalent, as always. So now there are two properties. So you have your f si omega so inside here you get the part corresponding to B SIB. This is contained in PI. Sorry. So you can check that this is an isomorphism. Okay, so the map is birational. The claim is that this map has connected fibers. So again, the situation is very concrete, so you can check by n that the fibers are connected. And now for the, say, the conclusion of the proof. The length of Si omega is less than the length of omega, so this guy is normal by induction. Look, the pi cross b xi s si omega has a natural map on pi mod b, so you check that it is pi equivalent with respect to multiplication on the left. This is a p1. And the typical fiber is exactly B cross B x si omega, that is x si omega. So you have a fibration of a P1 with fiber x si omega. So this guy is normal as well. B. Okay. So now, okay, so this is normal variety, this is also a proper variety. Right. Now, since this is a normal variety, this morphism factors through the normalization of x omega. So there exists a factorization from x si omega to the normalization so here you get this one as connected fibers. So this was as connected fibers. You know that the morphism is birational. So in fact, this one has to be bijective. And you know that x omega is weakly normal. Okay, so any finite birational and bijective morphism has to be an isomorphism. So here we use the fact that the x omega is split. So the second point of the theorem is for the rational singularities. So we need to prove three statements to get the fact that it is a rational resolution of singularities. The first one is the Ri of this is pi omega of O of z omega has to be 0 for I positive. Something that it is always true in a characteristic 0, but not always true in a positive characteristic. The same condition, but for the canonical class, this must be 0 for I positive. And finally, we need to prove that the push forward of the structure sheaf is exactly the structure sheaf of x omega. So for the point C, we know that pi omega is birational, and we have just shown that x omega is normal. So as pi omega is proper, we get exactly this statement. So it's okay. For B, this follows from some theorem we saw yesterday. We saw exactly the vanishing of the relative anticanonical class, assuming essentially that we have a section vanishing along the exceptional locus. And this is exactly what we get. We know that over the Breuer cell, we have an isomorphism. So the exceptional locus is exactly the union of the z omega j. So we get this for free. We saw the theorem yesterday. So the only thing to prove is A. But again, So for A, again, this is by induction on the length. So you choose SI such at the length of SI omega exactly as before, and now you consider PI B. I should say in a different way. You consider a reduced decomposition, and you set V being, so you forget about the first one, L, so this has to be a reduced decomposition of omega. Now you consider Pi cross ZV mod out by B acting again on the right ear, on the right ear and on the left ear. So in the end, you know what you get. So you get from. So ZV is mapped into XV, so you consider the corresponding quotient, and finally you consider the map we considered before. This is exactly the same. So by induction, so the corresponding I are 0 for this map, since the length of V is less than the length of omega, and here this is essentially the product with the resolution of singularities. So you can check easily that it follows from the induction that this is 0. And for this one, so for instance, you can show that this map can be decomposed as first you look at Pi. So this is not Pi, this is Pi1. So this is Pi1 mod out by B cross XW, and here you get the second projection. So here the claim is that this one is an embedding, but here you get a commutative diagram, and so the map sent a class GX to on the one end GB, and now GX, so you get something X omega. So the claim, and it's very easy to check that this is an embedding. Okay, so this has no higher direct images, and here this is a projection, and this is a P1. So here the I is 0, and here this is a projection, and the fiber is P1 again. Ri are 0 for I positive. So this has nothing to do with the positive characteristic of Frobenius splitting. And in fact, you can deduce exactly the same result in characteristic 0, since the only thing you need in some sense is vanishing theorem. And you can deduce the vanishing theorem from characteristic P to characteristic 0, essentially as Carolina explained in her talks. So if you have the vanishing for almost all P, you can get the vanishing at the generic point. Say as a corollary of that, of the fact that X omega is split, for M, an ample line bundle on X omega, then L has no cohomology for I positive, and as we have shown that X omega is Cohen-Macaulay, also this is 0. For I less or equal to the dimension. So I promised yesterday that I will use the D-splitting with respect to some effective divisor. So I won't do that because you need to work more, in fact. But I will state what you get using this D-splitting theory. So this is a theorem. The last one, due to Lauritsen and Thomsen in 2004. So this is for positive characteristic. It was already known for p equal to 0 and due to Kumar. I don't know the year. And it says that if L is a numerically effective line bundle on Z omega, then so you get that the cohomology, so this is at the level of Z omega, the Bode-Samuelson varieties, L, you can subtract G to the Q to the R of G omega G. This cohomology is 0 for I positive and Q less or equal to R less or equal to L and 1. So you have all this vanishing, and in particular L itself has no cohomology. And to conclude, I should say that if you want to learn properly all these things, there is a very good reference. This is a book by Brion and Kumar. And the title is Frobenius. Splitting method in algebraic geometry and representation theory. And I stop.